In the last video, we introduced some terminology for a mass spectrum, and in this video what we're going to focus in on is the isotope ratio for our molecular ion and how that can provide some vital information in determining what elements might be present within your molecule. This is especially helpful when you have a complete unknown and you're not even sure what kind of elements would be present in your compound. So in this video we're going to look at that molecular ion and the isotopes. So one quick and easy thing we can do is apply what we call the nitrogen rule. And the nitrogen rule simply says if you have an odd molecular ion, and this applies for electron ionization only, this does not apply to an ESI spectrum. But in an electron ionization spectrum, if you have an odd m dot plus nominal mass, then you have an odd number of nitrogens. Now this could be 1, 3, 5, 7, we don't know how many nitrogens, but we know there's an odd number, which means there's at least one of them. If you have an even molecular ion nominal mass, that means you have either no nitrogen or an even number of nitrogen. So you could have 0, 2, 4, 6, 8, we're not sure. But again, we know we either have none of them or we have an even number. So that's a quick piece of information that we can get just from applying or just from looking at the nominal mass of the molecular ion. The next thing that we're going to look at is the isotope patterns. Okay? And so when we look at isotope patterns, we're going to want to look at the m dot, our molecular ion, our m plus 1, so that plus 1 isotope or the plus 2 isotope, and compare that to what we know about naturally occurring isotopes. So let's look at some naturally occurring isotopes. Okay? We know that we have hydrogen and deuterium, where deuterium has one extra neutron. Now hydrogen 1 occurs 99.988% of the time. Deuterium is only 0.012%. We can also have carbon 12 and carbon 13. Carbon 12 is more abundant, but we do get about 1% of carbon 13. Now what you'll notice is if this is 1% of carbon 13, that means 1% of the time our carbons are going to actually weigh more than 12. So when we think about this ratio of our molecular ion to our 1 plus isotope, this would be if you have one carbon that's a carbon 13. If you have 100 carbons in your molecular ion, this peak will be at m plus 1, will be about 1% of your molecular ion. So when we do interpretation, we can look at this ratio and determine approximately how many carbons we might have if we've determined that we're only doing hydrocarbons. The bigger the molecule, the bigger your isotope peaks are going to be, such that when you get up into the thousands, the probability that you're going to have multiple carbons being carbon 13 actually becomes quite high, and the likelihood of having all of your carbons be carbon 12 becomes quite low. And so for very, very large molecules, we're talking thousands of Daltons in size, you might actually see the m plus 1 peak and consider that to be your molecular ion when in reality it is actually representing an isotope. Okay, so when we're looking at these carbons and hydrogens, again, we're looking at what are the combinations that could get us to a higher mass to charge. And so let's just take C2H4 as an example, our ethene molecule. And so in this case, we could have a carbon, or we could have all carbon 12s and all hydrogen 1s, and this would lead us to our m dot plus. Now if we switch one of those carbons for a carbon 13, Now we have an M plus 1, right, because we're one higher. We could also get this by having all carbon 12s, and 3 of our hydrogens are hydrogen 1, and one of them is deuterium. This would also lead us to an M plus 1. Now getting to a M plus 2, we would need to have either 2 of our hydrogens being deuterium, or we could have 2 of our carbons being deuterium, being carbon 13, and all of our hydrogens being hydrogen 1, or we could have some combination where you have a carbon 12, a carbon 13, 3 hydrogen 1s, and 1 deuterium. Go. All of these would lead you to the M plus 2. So you see, as we get to be as our molecules are much larger, the likelihood of getting to an M plus 2 or an M plus 1 gets higher and higher. Now, these aren't the only ways to use isotopes. One of the really common ways to use isotopes is actually in identifying chlorine and bromine. So chlorine has a really interesting isotope ratio where you get chlorine 35 about 75.78% of the time, and chlorine 37 is the other 24.22%. What that means when we look at our molecular ion to our M plus 2, because this is a plus 2, means that our M plus 2 is going to be about 1/3 the size of our molecular ion. And that's due to this ratio where we have 3 to 1, so it's kind of a 1/3 size. Now the other one that's really interesting that we look for is for bromine. Bromine is bromine 79, 50.69%, and is bromine 81, 49.31% of the time. And so your M dot, or your molecular ion, and your isotope ion for the M plus 2 are about equal in size because the probability of having each of these isotopes is very, very similar. So if you are looking at your mass spectrum and you see an M plus 2 peak that is about 1/3 of the size of your molecular ion, that's a good indication of having chlorine. If you see that the M plus 2 peak being almost equal to your M dot plus, that means you probably have bromine. So using the nitrogen rule and the isotope pattern, we can very quickly start to determine, are we looking at having nitrogens present? Do we have chlorine? Do we have bromine? And what's our approximate number of carbons based on the M plus 1 peak? So these can be particularly useful in determining what atoms are present in our unknown sample.